Okay. All right. Let's start
Yes.
the last session. Okay. Yeah. The first talk is a remote. That's our second one, and it's a short talk. And another talk, I will start with panel. Okay. So next talk is type-sensitive algebraic macros. Who's giving the talk? April. Okay. All right. Please start.
Oh, hello. Good afternoon. I'm April, and I'm giving this talk on type-sensitive algebraic macros. It's work with Robert Atkey from the University of Strathclyde. So I'm going to start telling you that the goal of this project is to introduce metaprogramming with algebraic effects and handlers to language with dependent types. But here I will start working with the well-known STlC. Some people in the audience might have heard something in the lines of what I'm going to present. It's because Robert Atkey has already presented this about 10 years ago. So we are picking it up again. So let's get started. So let's start by having our simple STlC type checker. And then rather than having it in your regular implementation as we would do in Haskell, we slice it, and rather than pattern matching on specific constructors, we have each of the constructors being its own function. And we also add a couple of other constructors like have, which means to assign a type to a term, and has type, where whether in this case where you can assert what a term has this type, and then now we have type checker operations. Now with those operations, we can write some programs. Here we can write a program that is just an assertion. We first assert that it has a specific type, and then we write the term for it. And the second example, we have the same assertion, but it also has a hole that we can pass in another term. And we can have multiple assertions with holes. And then looking at those programs, you may ask yourself, wait, are those macros? And the answer is yes. Not only because it was in the first slide, but that's what we are trying to get done here. So, but now let's get serious with the work we are doing and start implementing those algebraic macros in Agda. Here we have, again, the algebraic macros for STlC. In Agda, I have highlighted some of the implementation, just showing you the types and how it would work. And with that, we can start to write programs like this one, where we can assert a goal. The definition of goal is shown on the first line. And we can basically show that this term has this type. And also we can, with this macros, we can also start introducing tactics that are well known in a programming language like Rock. So we can here have intro, where we introduce a variable v1 and v2, and we have, and to prove the application, we have the assumption. So I want to make it explicit here that we are using a higher order abstract syntax, and we hide universe levels in Agda. If you're looking at this code and thinking, oh, this is not going to work, it's because we have removed the levels to make it easier to read. So we have implemented this, and can we do more than type checking with this? And the answer is yes. We can implement elaboration as well. And here, giving a list of types, we may have a type and a new term that is type correct. And right now you may thinking to yourself, how would this scale to other type theories? And my answer is, of course, in a sense that I'm hopeful that I can answer this, but we are in the process of extending this to other type theories. But here I can show you that it works for the bidirectional STlC. For those who are not familiar with bidirectional, the idea is that type checking has two judgments. One that the terms can be checked against a type, and also that giving a term, you can synthesize a type for said term. And here we add switch and ascribe, which are operations that are related to the that are necessary for this bidirectional implementation of STlC. What we gain in this when we do this is that we no longer need to talk about what the goal is and what the term is. We can just use introduction and goal. And one application for this is was shown in eCoop 2014 by Omar et al. That if you have different types of constants, for instance, a string that you want to interpret as HTML or Markdown, so you could implement this elaboration in using our algebraic macros. You might be asking yourself, what is algebraic about this macros? And the answer is that it basically forms an algebra of a type theory. So we have our operations that vary depending on the type theory. And we have equations. Here the equations have a little alert emoji because we haven't proved that those equations hold for this, but we are in the process of doing it. And also we can extend it to contain models, and models are another name for handlers. So the idea of algebraic macros fit perfectly the theory of algebraic effects and handlers. Now let us go one step up and implement this in a type theory that has unification. Here we do it by implementing macros for prologue style inference. And here we introduce meta variables. And we are able to introduce those new meta variables to the context with the new operation, and we have the unify operation that unify two types, and choice that is very common in prologue style inference. With that, we can write a tactic by assumption, where we can search for this unification and choose whether to unify or continue to search along the context. So with this, we can show that our system is flexible enough to do more interesting stuff than STlC. So in the future, we are working on, as I said before, showed the equations for each theory hold. We also have started extending this for system F omega, and finally we want to extend this for dependent types. Finally, if you want to see the implementation, it is on GitHub, and we have as well a playground programming language that we are implementing this and other stuff. And this playground language is implemented in collaboration with Gonçalves, and who's an independent researcher, and Paulo Torres from the University of Kent. You can use this QR code to get those links. That's it for me. Thank you so much.
Thank you. Any questions? Okay, let me start with one, actually. So you start with saying you picked this up after 10 some years. What's the motivation for that?
I was working for some time on a programming language, and we are the Bentley type language, and we were trying to implement metaprogramming, the style of the elaboration monad and the TC monad in Agda. So we thought that if we could extend it for algebraic effects, maybe we could get a more composable way of doing metaprogramming in the Bentley type language.
Hi, April. Thanks
Hello.
for the talk. There's Sam Lindley here.
Oh, hello, Sam.
You mentioned, well, relating this to algebraic effects and effect handlers. Have you considered extending the simply typed lambda calculus to a language which itself has effect handlers in?
Oh, no, we have not. That's a good idea. That would be fun.
Thank you. Next question.
Hi, I wonder, so you choose typechecker as the main demonstration, and there were papers using like applicative or monadic structure to implement the type checking and elaboration. So how would you like compare your work with them, like using
So this is so we have a bunch of this work has already been used in languages like Agda and Idris, and I believe also in Rock. I think MTAC is has a monadic approach. The idea is that by using algebraic effects, you could choose to use your handler. So you can choose to use type checking or elaboration by choosing a different handler, and that's where we believe that this approach can bring us further in the process of using metaprogramming, because then we don't have to, theoretically, we wouldn't need to write a type checker and a elaborator separately. Yeah, I hope that answers.
Any more questions? Okay, now let's thank the speaker again.
Thank you so much.